So, good morning, welcome to this class on Neuroscience of Human Movement. So, in today's class we will be talking about Nernst Equation. We described a situation in which forces across a semi-permeable membrane could balance each other, and what could happen in such a situation, or an equilibrium is created, and we suggested that there is a potential at which this equilibrium is achieved, and we call this as the equilibrium potential for that ion, or the electrochemical equilibrium is achieved, and equilibrium potential is the potential at which this electrochemical equilibrium is achieved, right. So, how to compute this? This is achieved using Nernst equation. So, in today's class we will discuss this. So, here is a situation when there are two solutions separated by a semi-permeable membrane. So, here is a semi-permeable membrane. There is solution 1 and solution 2. Solution 1 has a higher concentration of sodium. So, the font size here represents concentration, or a higher font size means a higher concentration of sodium and chloride in solution 1, whereas in solution 2 you have a much lower concentration of sodium and chloride, right. Suppose this semi permeable membrane was permeable only to sodium. So, this is a sodium selective membrane. If that is the case, then what happens is that only sodium diffuses across this membrane in that direction. Chloride cannot diffuse because this membrane is permeable only to sodium and not to chloride. But since only sodium is diffusing, this causes a buildup of positive charge on the right side, like that. If only chloride was also able to diffuse, you would not have this situation, but in this situation when sodium alone is diffusing, you have a buildup of positive charge in solution 2. If sodium was not charged, if sodium was not an electrolyte, if sodium was not an ion, if it was a non-charged solute, right, then in that case the movement of this substance would be driven only by concentration gradient, and that will not build any charge in the right side, right, in solution 2. That will not happen because that we are discussing does not have any charge. So, it will not build any charge separation between the two sides. But however, since sodium is an electrolyte, is an ion, what happens is that in the transport of sodium across the semi-permeable membrane builds this charge separation. So, on one side you have positivity, on the other side you have negativity. So, what this creates is a potential gradient, right, a potential is developed. So, now in this case the transport of ion is governed by two forces. One is the concentration gradient related force, or the force due to the concentration gradient, and the other is the force due to the potential gradient. Note that the potential gradient itself may be developed due to the movement of ions, which happens due to the concentration gradient, but as the sodium continues to move, further addition of sodium is resisted by the positive charge that is present here, and this resistance to further movement of sodium increases as the amount of positivity on the right side starts building up. So, initially there is less resistance, as you go along the resistance is very high, and at some point what happens is that the sodium ion can no longer go from this side to that side. It is not possible for that movement to happen, for that transport to happen, because the positivity on the right side is sufficiently high to repel any more entry of cations, any more entry of positive ions or sodium in this case into the right side or into the solution 2. The potential at which this happens is the sodium equilibrium potential, and that equilibrium is called as sodium electrochemical equilibrium, right. So, that is the sodium electrochemical equilibrium, and the potential at which it happens is called as the sodium equilibrium potential. Now, let us consider this situation one more time. So, suppose there is a greater number of particles or solute particles on one side, and let us assume that these solute particles are charged, these are ions, right. So, here as you see, the right side has a higher concentration and the left side has a lower concentration of this particular solute, right. Let us assume that we also know the concentrations, these concentrations C1 and C2, or in other words C2 is greater than C1 is something that we know, but we also know the exact values of C2 and C1. Let us see. Also I know, for example, the voltages between in this chamber and in that chamber as V1 and V2. If there is transport across this semi permeable membrane, let us assume this is a semi permeable membrane. If there is transport across this membrane, it turns out that the force due to concentration gradient will move these ions in that direction, right. Let us assume that the potential gradient is in the opposite direction, suppose. Now, the question is it possible to develop a relationship such that we are able to compute the point at which the balance occurs or the electrochemical equilibrium is achieved? Can I somehow compute this? It turns out that it is possible for me to develop expressions individually for each of these forces Fc and Fe, and that is, these are already known. This is the force due to the concentration gradient, that is RT ln C, and the force due to the potential gradient is ZFV. These are already known, where R is the gas constant, T is the absolute temperature. So, in Kelvin, right, or the temperature at which the computation is performed, or the temperature at which these chambers are. So, that temperature T in Kelvin. For example, in humans this would be 37 degrees Celsius or 310 Kelvin. So, appropriately we will have to substitute that value. It can be different in different organisms or in different situations. So, you will have to consider that, and Z is the valency or the charge of the ion. This can be +1, -1. For example, for calcium this is +2, etc. F is the Faraday's constant and C is the concentration of that ion and V is the voltage, right. And it turns out that I could come up with the equation that balances these two, that is this equation, that is basically Fc1 plus Fe1 is equal to Fc2 plus Fe2. So, these two forces, the sum of these two forces exactly balance each other at some point. The question is, what is that point? That is what we are interested in finding out. What is the potential difference or what is the concentration gradient at which this will happen, right. In particular, we are interested in computing this potential at which this happens, right. So, in this state of equilibrium, what happens is that although there may exist a concentration gradient, there will be no more movement or no more net movement. It is possible that in the previous case, one ion goes from right to left, suppose one ion goes from right to left. It is also possible that the probability of another ion moving from left to right is also approximately the same, such that the net force or the net movement is approximately 0, right. So, that is the situation. So, in the state of equilibrium, the net movement is approximately 0 or the movement of all particles are counterbalanced. So, there are no net changes in concentrations anymore. Although there may exist a gradient, this cannot be further changed because of the potential gradient, right. So, that is the situation. So, if we are considering the cell membrane and the outside of the cell membrane and the inside of the cell membrane, I could rewrite these equations and this equation as this, right. Suppose the concentration outside was C out and the concentration inside was C in, the voltage outside was V out and the voltage inside was V in. I could rewrite this, and a simple rearrangement of that equation gives me this, right. So, basically I am taking the concentration terms on one side and the voltage terms on the other side, and then I am naming this difference as V equivalent, right. This is minus, because V equivalent is V out minus V in. So, basically Z of V equivalent will give me minus RT ln C in by C out, and so I am interested in knowing this value V equivalent. So, effectively Z f comes to the denominator as it does here. So, that is the equation of interest for us, right. So, this equation is called as Nernst equation, and it is useful in computing the equilibrium potential of individual ions across the biological membrane. It is critical to note that this is only when considering one ion at a time. Suppose there are multiple ions, right, the situation will vary. So, for this equation, for this situation, we are only considering one ion at a time, right. So, that is the equilibrium potential, and I could for example convert the ln here as log. So, using this multiplication factor, and I know R T for example, I know F, the only thing I do not know is Z, which changes depending on which particular ion I am considering. So, I could theoretically compute all these numbers. I also do not know C I and C E, of course, I also do not know these things. Only those that I have marked in red are unknowns, those that I have ticked are all knowns, for example. These are all things that I already know, right. So, I could compute what that value would be, right. So, that is this, right, this is minus 60 divided by Z at 310 Kelvin, at 310 Kelvin. Once again note, this is assuming T is equal to 310 Kelvin, right. I could analyze this for various ions and for various concentrations. Let us do some example problems, right. The intracellular concentration of sodium is 14 so many milliequivalent per liter, and the extracellular concentration is 140 milliequivalent per liter, for example, right. And we already said that the Nernst potential is minus 60 millivolts by Z, log based on Ci by Ce. So, I can substitute Ci as 14, Ce as 140. Once again this is computed at 310 Kelvin, let us remember that. Suppose the problem asks you to compute this for a different temperature, then you have to go back to the general form of this equation and redo this problem, right. So, but at 310 Kelvin you could substitute for these values as we have done here, 14 by 140, 14 by 140 is 0.1 or 1 by 10 or 10 power minus 1, like that, and that basically means this is 60 times log 10 base 10, is it not, which is 1. So, that is actually plus 60 millivolts. So, what this means is, if the membrane potential were at plus 60 millivolts, then there will be no more movement of sodium across the biological membrane. If ever the biological membrane reaches a potential of plus 60 millivolts, sodium will not bother to move from this side to that side, or any movement of sodium from side 1 to side 2 will be counterbalanced by movement of another sodium ion from side 2 to side 1, for example, or there will be no net movement of sodium from one side to another side, or from intracellular matrix to extracellular matrix. It is not necessary for the sodium ion to make a movement. So, ideally this is the potential at which the sodium ion would like to have. Suppose the sodium ion has a mind of its own, suppose it had a mind of its own, this is the potential at which the sodium ion would like to have the membrane at. So, if at all it is possible for the sodium ion to have a wish, then it will say, okay, let us have the membrane potential at plus 60 millivolts, Why? Because this ion is lazy, it does not want to make any movement, right. So, let us consider the situation for potassium. Right. Let us remember we discussed the typical concentrations of potassium sodium chloride in an earlier class. Let us remember that the concentration inside was approximately 120 milliequivalent per liter and outside is 4 milliequivalent per liter, is it not? Now, once again I could substitute this. So, again the problem is to be solved at 310 Kelvin. Now, once again let us substitute the value of Z, which is plus 1 here, and substitute for Ci and Ce, which is 120 and 4. So, when I do that, so this is actually 30. So, I could compute log 30, right, and so then the equilibrium potential comes out to be minus 88 millivolts. So, once again, so this is the potential at which there is no net movement of the potassium ion across the biological membrane. So, if the potassium ion had a mind of its own, it will prefer to have the membrane potential at this value because it does not have to make any movements. So, this is where it would like to have it, but where is it? Where is the membrane potential relative to its equilibrium potential will determine to what extent the movement is happening, that we will reserve for future classes, right. Similarly, for chloride, once again I know the inside concentration as about 10 milliequivalent per liter, the external concentration is about 150 milliequivalent per liter, and the problem is to be solved at 310 Kelvin, say for example. Then I could substitute for Ca and Ce and Z. Note Z has a sign. So, here I will have to substitute for Z as minus 1. So, this is crucial. So, when it comes to sodium and potassium, since it is plus 1, we did not really care to substitute that because anything divided by plus 1 is the same, it does not really matter. However, when it is chloride, it is important for you to substitute this as minus 1, not as 1, because then the answer will be very different, right. So, I am substituting this by minus 1 and I am solving this problem, proceeding to solve this problem. I am substituting 10 there and 150 there, right. And so, that will basically give me the equilibrium potential for chloride as minus 70 millivolts. Once again, this is the value, right. So, this is the potential that the chloride ion would like the membrane to have, because at this potential the chloride ion does not have to make any movement. So, it can be lazy, it does not, or the net movement of ions across the membrane will be 0, right. So, this is ideally where the chloride ion would like to have, but once again the difference between the actual potential and the equilibrium potential will determine the movement. Okay. So, let us remember the concentration. So, 14 and 140 between inside and outside. So, the equilibrium potential is plus 60 millivolts. For 120 and 4, the equilibrium potential is about minus 88 millivolts. Once again note this is the calcium concentration inside and outside. So, the equilibrium potential is plus 120 millivolts. So, for calcium Z is equal to plus 2, remember. So, also note that in the exam problems the actual numbers may vary. So, you will have to substitute appropriately. These are some examples that I am giving. So, this is 10 and 150. So, the equilibrium potential is minus 70 millivolts. So, what is the driving force? What constitutes, what causes the movement of ions across the biological membrane? That is, as I said, the difference between the membrane potential, between the actual membrane potential, which is Em, and the equilibrium potential, which is Ex. So, the larger this value is, the higher is going to be movement of that particular ion. Suppose Em is say minus 80 millivolts, right. Let us go back to the previous slide and see. Suppose Em is equal to minus 80 millivolts, right. Then in that case, which of these ions will have large movements, which ones will have small movements? This one, right, will have small movements. Why? It is already close to its already the membrane potential is close to the equilibrium potential, whereas these two will have large movements, right, or in other words, if there is possibility of an opening, if there is possibility for movement to happen, then a large amount of movement will happen, right. So, something to remember. So, relatively this will also have a small amount of movement. Okay. So, with this we come to the end of this lecture. We will continue the discussion in future classes. Thank you very much.